Welcome everyone to week 2. We have a few new people here, so welcome. We're going to have a lot of fun. Let's just jump right in. So I'm going to tell you about the PNT Plus project. Again, yeah, this was kind of what we discussed last week about how, there's underlying lean. I have to get used to this quasi pointer. There's underlying lean. On top of that is built this great library, and then you can do sort of research and teaching. And the prime number theorem project, it's not exactly research. We're not really learning new things about the prime number theorem, although I'll argue that some of the things we're doing really are, it feels like research. It's not exactly teaching because, it's not, it may eventually actually become a really good place to learn the prime number theorem. So it might be a resource for teaching. But hopefully, eventually, we will do it in a way that's good enough to get into Mathlib. But right now, we just want to do all kinds of things. So the project was started, I guess, about a year and change ago, and in about 2 months, we proved the original. The first goal was just to get the prime number theorem. So let me say more about that. So the project was co-organized with Terry, and the goal is, Kevin Buzzard, I don't think is a secret that Kevin Buzzard is running a 5-year-long project to formalize Fermat's theorem, at least down to things that were known in the 80s. And one of the ingredients is Shepard density theorem, which of course was known in the maybe not 1880s, the late 19th, early 20th century. And a special case of that is Dirichlet's theorem, just primes and progressions, and not just their existence. Actually, all he needs is their existence, but we want to count primes and progressions, and we at the time didn't even have the prime number theorem in Mathlib, so let's do it. Let me point out that the prime number theorem has been formalized many, many times in many different systems. Jeremy Avigad gave the first one already 20 years ago. What we want to do is do it in a way that will extend to much more general settings, setting things up for Shepard. And the way that we're going to organize things, so I'll spend a bit of time at the end talking about that, is using a combination of GitHub to pass code back and forth, Blueprint to organize what kind of code we want to write, and Zulip to organize who's going to do what and how we decompose the various tasks. So the original project, the way we envisioned it, at least in this first direction of just getting ever stronger versions of the prime number theorem, one was just using Fourier methods. This is the Wiener-Ikehara-Taberian theorem, if you know what that is. Basically, you go up to the one line, but you don't ever cross it. So you can already get the prime number theorem without doing any actual complex analysis, just from Fourier analytic methods. Then a medium strength prime number theorem, we developed techniques of Mellin transforms on top of API that David Loeffler had added to the library. And we're going to pull infinite vertical contours past this one pole at s equals 1 and pick up a residue, but we're not going to do it in sort of the most, we're going to do it in a way that gets us an error term that's good enough for every application I know of, but not one that gets you the classical error term, for which you need something like Hadamard factorization or local versions of Hadamard factorization, which is a little bit more complex analysis that I want to do. I wanted to do enough complex analysis to do a contour pull, but not so much complex analysis that we get the full strong version. In the meantime, so a paper posted around mid-March 2024, these two, I think one was an undergraduate and one was maybe a high school student or something, proved the strong version of the classical error term for the prime number theorem in Isabelle. And they're building on top of the fact that Isabelle has this massive complex analysis library that Mathlib is still. Mathlib is in a funny, so if you want to do complex analysis, the first thing you do is you draw, if you don't want to use the Jordan curve theorem, by the way, they have the Jordan curve theorem in Isabelle, and it's 10,000 lines of difficult code that the Mathlib people say, well, it's just a cohomological statement. You develop enough, you just apply. I mean, this is what we were discussing before. But Mathlib says that, and then so we're waiting all these years for that cohomological statement to be available, so that Jordan curve theorem is just an immediate consequence of that. But we're still waiting. So in the meantime, we're going to do something else to get around that fact. So let me tell you what that is. Right. So on top of just getting the prime number theorem into the library, it was a great excuse to do all kinds of other things. We didn't even have Fourier inversion, which we now do thanks to Sebastian Gazelle. We didn't have that the Fourier transform of a Schwartz function is Schwartz. This is a combination of Heather's work, David Loeffler, myself, and Vincent Bafara, and Sebastian. And again, we didn't have complex analysis. And the big idea that led me to think that we would succeed in this project when we were first envisioning it, because I had a little bit of experience with complex analysis in Mathlib, or trying to build something for Mathlib. And it was tricky. It was tricky. And then I realized, actually, it doesn't have to be tricky. All we need is rectangles. So with the only contour analysis we need is rectangles. And let me show you how we do that. So we define a rectangle given two corners, Z and W, two opposite corners, to be the interval between the real parts across the interval in the imaginary parts. And then what is an integral over a rectangle? So it's a horizontal integral along the real parts at the height of the first one, minus the horizontal integral on top, plus the vertical integral. And how do you do horizontal and vertical integrals? There's API for interval or integration. So this is an integral in between these two real numbers, x1 and x2, and the function is evaluated at x for a fixed value of y, for a fixed height y. And the vertical integral is similar. So you can imagine defining these things, having API for these things, and now you can do rectangle integrals. Okay, stop me anytime if you have questions. I'm going to go through this stuff somewhat quickly. There's no clock in here, so I just have to keep an eye on the time, because I want to get to the lean and not the mathematics. The mathematics is going to go a little fast, because not everyone here is a number theorist. This will be at a perfect pace for Max. But if I lose some of you, that's okay, because there's a whole blueprint that describes what's going on. And hopefully, if I've done my job right, I'll decompose the tasks to things that are small enough that you don't actually have to know any complex analysis, any number theory. The task should be just exercises in lean and maybe real analysis or baby calculus, things like this. Okay, so then this we have Green's theorem, thanks to Yuri Kudryashev, and we know, therefore, that the integral of a holomorphic function over a rectangle is 0. So this is what that looks like. So in fact, you're going to do it in the generality of integration on normed additive commutative group E, which is also a complex normed space. Whatever those things are, I want to be able to take
spaces.
Banach spaces, right? Exactly. That would be the better way to say like we have vector spaces or modules with over a field. This is a better way to say Banach space. Okay, so we have a function from the complexes into a Banach space. We have two points. We assume the Banach space is a complete space, and we have some set. And we assume that the rectangle with corners Z and W is contained in that set, and F is holomorphic, meaning complex differentiable on that set. Then the rectangle integral, which is what we said it was, vanishes. Okay, so that was step one, was kind of already there. Step two was to get a residue theorem for rectangles. And this was really fun. I will not, in the interest of time, go into how we prove this, but I'll draw one picture, which is that usually what you do if you have like a function that's holomorphic on a disk minus a point, and you want to get a residue at this point, one of the standard arguments is to do something like this, say, oh, the integral is 0 over that bit, and then you can zoom in on this circle. But can you imagine how annoying it would be to try to code this up? What exactly is going on here, and where the point is, and how do you get to it? Now think about rectangles. You know that the integral over a rectangle is 0, and you have some point here. So you just do this. And these rectangles are all 0 because it's holomorphic there. And then you've zoomed in onto a square. And once you zoom in, then you can do a very simple calculation, which itself is really fun. But again, I'm going to skip that. You can read the blueprint for how it's done. So the point is, once we have to actually know in which corner is which. So Z is the lower left corner and W is the upper right corner. And this rectangle is in the neighborhoods filter of the point P, which means there's an open set that contains P that contains this rectangle. Okay, so P has an open set that contains the rectangle, and now we can get going. And that's kind of a nice way to say it. And the hypothesis is that we know what the principal part of F is. So if we have a simple pole, so the function F minus A over S minus P, this is the pole, this difference is equal to G on the rectangle away from the point P. So we assume we have a holomorphic function on the entire, I'll write it here. Can everyone see if I write in the middle here? So we're assuming that this is not actually, okay, that's a little trick. So we're assuming that f is equal to some constant over s minus p plus a holomorphic function g, where g is defined on the whole rectangle. And so you say f minus the principal part is equal to g on everything but that point. Then we can integrate, and the prime is that we've divided by 2 pi I. That's another little annoying thing that comes up all the time. The integral of f over that rectangle is the residue, is the constant A. Okay, so we have that much of the residue theorem. This has not been PR'd to Mathlib yet. And there's a question of whether this belongs in Mathlib. This is the wrong theorem because it's just for rectangles and we want things, you know, for general curves, yada, yada. So that's one of the issues you get if you want perfect code that goes into the library, or if you just want to work and do something and never mind whether it's good enough for the library. We just want to get something.
Just a question.
Please.
So the first picture was done in Isabel.
The first picture was done in Isabel.
Was it? Yeah.
Oh, I don't know how Isabel did it. I know that Isabel has a big complex. Once you have the general Jordan curve theorem, which they do thanks to Tom Hales, I think. Tom Hales, I know, has a whole paper on the proof of the error in Jordan's proof of the Jordan curve theorem, which is not an error at all. It's just people didn't understand it. It's very technical. It's something like 10,000 lines of code. So imagine someone goes and sits down to do those 10,000 lines of code to prove the Jordan curve theorem. And then 6 months later, someone comes along and says, okay, I finished the homological version, so just erase your 10,000 lines. You're like, great, thanks. What did I do that for? Right.
But the strong, is this necessary for the strong PNT? Like the first picture?
Is this necessary?
I mean, is this sufficient? This is not sufficient for the strong PNT, right? Or
well, it's one of the ingredients. If you want to actually get a residue, if you want to go inside the critical strip,
this is already sufficient.
This is already sufficient. Yeah, with a bunch more work, but yeah, this is all.
So I don't know.
Yeah, that was the whole point. Was that we pull all kinds of contours in all kinds of funny ways, but then my realization was if you just want to do, you know, the things we do with L functions is pulling vertical strips, and in fact, we don't even pull infinite vertical strips. We only pull, although we can pull vertical strips now. That's part of the API that we developed to do this kind of thing. But we actually only ever pull little rectangles. And if you control rectangles, you control the world. Next.
Where are the objections from Mathlib for just doing rectangles? Because I think 95% of analysts only ever touch rectangles.
So I should say, it's not that there has been an objection. We haven't tried to put this into Mathlib and see what the conversation is. The informal conversation has always been, we should do complex analysis the right way, and the right way is with Jordan curve, and the Jordan curve theorem takes this homological. So there's this long chain. This is something, what's that?
It's not true that the right way is the Jordan curve. So,
there are
I will
analysts that say that the Jordan curve is extraneous to the residual theorem.
it is extraneous in a sense.
It's homological theorem, the residual theorem, not homotopical.
Yeah, so we can argue about, but I will say that I first heard Kevin Buzzard talking about Lean and Mathlib in the fall of 2019, I think. And I was teaching complex analysis, and he said, we don't have complex analysis. And I said, oh, great, I'm teaching it. I'll just, you know, every time I prove a theorem in class, I'll prove it in Lean. And yeah, here we are 5 years later. So, okay, we can do rectangles, and rectangles is all we need to do. There's something really fun that happens. I'm not going to go into it, but it's really, if I encourage those of you who are interested in this to read how we prove this theorem, because this is what I mean by it feels like research. Like we came up with a rather neat fact that happens that's kind of an accident. Oh, right. Sorry, question? No?
Sorry.
Oh, that's okay. I just wasn't sure. Any questions, please, at any time interrupt. Yes?
Can you say what the set econ syntax is doing there quickly? I think you said
set econ is that the two functions are equal on a set. That's all. So the function f minus a over s minus b is equal to, pointwise, the function g on the rectangle take away the point b.
Oh, I see. So the fun syntax is a map from S.
Oh, yes, I'm sorry. The fun is how you define a function. Yes, f is already a function. Now I'm going to define a function on the complex numbers to the complex numbers. Yeah.
So does we treat this as like a definition of G?
No, G is given. I'm given f. This pointer really is not that great. Here we go. I'm given f and I'm given G. So I assume I have G, and I assume there that G is holomorphic on the whole rectangle.
Yeah, okay, sorry, I understand. Okay, thanks.
And then how do you find such a G? Well, we have the Riemann removal singularity theorem, which is that if if S is a set in the neighborhoods filter to C, S contains an open set containing C, and the function f is holomorphic on S take away the point C, and it's bounded above. So if a function is bounded in a neighborhood of a singularity, then it's not really a singularity if you're holomorphic. Then there exists a holomorphic function on the entire set, and which agrees with f on the set minus the point. Okay, so if you can prove that you have a function f for which f minus, so when you take f and you subtract off the principal part, you're bounded, then you get your G from the Riemann removal singularity theorem. Okay, so that's going to be important because that's exactly what we're going to do with the Riemann zeta function. Okay, that was complex analysis. Let's do a little bit of number theory. Everybody's okay? I realize it's Monday morning. It's hot outside. Let's go. Right, so the most important thing to start with is the von Mangold function. Here's the classical definition. It's log p if n is a power of a prime and 0 otherwise. How it's implemented in Lean is really interesting. There was a long discussion about the fact that, should you use, let me save that discussion for just a second. So the way it's implemented is as an arithmetic function. The local notation is meant to look like the classical notation. We want things to look like math. What is an arithmetic function? So there's an issue when doing L series that you want to say an L series is a sum of some coefficients divided by n to the s, n greater than or equal to 1. Well, it's okay in Mathlib to put a 0 because division by 0 is 0. 1 divided by 0 is 0 in Mathlib. Have we talked about this already? I don't remember. We had a conversation. Okay, not really. Like, why make these design choices that you don't want to make these types?
The fact that it's true, you said several times.
Okay, why it's true we didn't discuss. Yeah, maybe now's not. It's a long conversation. So maybe in the interest of time, let me just say that it's a fact that you want to. It's a fact that the choices we made to make operations like subtraction, like 3, the natural number 3 minus 7 in Mathlib, 0. Okay, so good. So it's not true that A minus B plus B is not necessarily equal to A. That's not a theorem in the natural numbers as subtraction is defined in Mathlib. Okay, it is a theorem if A is greater than B. So you need to know that whatever you're doing, and it's also a theorem if you coerce these up to from the naturals to the integers. So there's all these kind of subtle things. So you might say, what's the problem with 0? You just divide by 0. Well, S is 0. 0 to the 0 is 1. And so you get this really annoying stuff happening with 0. And so the decision was made to implement something called an arithmetic function. Instead of, there is a type of n plus. N plus is the natural numbers together with a proof that n is not equal to 0. And that turns out to be really annoying to work with. And so instead, what was implemented is an arithmetic function, which is a function that takes its input as natural numbers, but there's an extra hypothesis called zero harm. And zero harm is that if you have a target, a source and a target, and each of them has an element called 0, then the function is a zero harm if it sends 0 to 0. So R is an arbitrary type. All we're assuming about it is that it has a 0. The natural numbers have a 0, and this is the assumption that it sends 0 to 0. Okay, so as long as there's a 0 on top, it doesn't matter what's happening on bottom. We can sum over the natural numbers. So basically, it's just a way of saying it's a sequence defined in the natural numbers. So we don't we're not going to play with. We're not going to assume here. we're not going to assume at the level of the input that the natural number is not zero, but we will assume at the level of the series that the 0th term in the series is 0. That was a subtlety that was worked out by Michael Stahl to make things work. Okay, so that was an implementation decision. Then what we want to do is sum the primes up to x, weighed by log, primes and prime powers. That's the main object in the prime number theorem, implemented exactly as you would do it as a human being. So you take, you want a sum up to x, maybe including x. I don't know. It doesn't. This less than or equal to versus less than sign makes no difference. We're going to do things asymptotically. So we'll take x plus 1. We'll take the floor that sends it into the natural numbers. There's also from the real numbers to the integers a floor, but we want to go into the natural numbers because in the natural numbers we have finite sets. The range, the finite set range of 10 is the numbers from 0 to 9. So that's why we'll go to x plus 1. And then we're going to sum this function along that range. Okay, so it's just a little bit of, I mean, I guess I said it looks just like that, but once you have enough dollar signs and backslashes in your mind, you see LaTeX as if it was a PDF. In the same way, you just start reading things like this and say, oh yeah, of course, that's what that means. And then we have local notation for it, the Chebyshev psi function. Okay, so the medium prime number theorem is that the psi function minus x, so it's asymptotic to x, we're not going to get square root log error, which is the classical error. We're not going to get the 3/5 error, which is the best known today. We're just going to do 1/10, and 1/10 is this x, e to the, maybe you guys aren't used to these number theoretic, e to the minus a constant log to some power. It's better than any power of log. And as far as I know, there is no application. Do you know of an application that doesn't work for this, but does work for 1/2? I mean, once you save 1,000 powers of log, you get everywhere. Okay, if you can find one, I'll be, yeah, think of one. I thought about it for 2 minutes and I couldn't find it.
I sometimes need Vinogradov's method. So the
okay, but,
sums,
yeah. So that's, yeah.
Which kind of gives you 3/5, but
right. So 3/5 is a whole other thing, right? That would be a whole other project to go to 3/5. But from complex, those are exponential sum methods as opposed to complex analytic methods. So that's a whole other project. Okay, so what does this look like in Mathlib? Here it is. Here's the theorem. You see it uses sorry, so we're not done with the medium version. The theorem is that the Chebyshev's function psi minus the identity function that sends x to x, we need functions, so it's the identity function, is big O as x goes to infinity, that's the at top filter, of the function that sends x to x times e to the minus a constant log x to the 1/10. Okay, how is big O implemented? So we have all of the language of, Landau and Vinogradov notation. F is big O with respect to a filter L of G if there's some constant, so that F is big O with the constant C. What does it mean to be is big O with C? So if you know what the constant is, then it satisfies this predicate if eventually in the filter, exactly as we discussed last week, if eventually in the filter, F is bounded by a constant times G. Okay, so everything really works in the language of filters and allows you to say things that look very much like how they look in natural language. So far, so good? Okay, so we have the fact that the Euler product, this is not, you can take this to be the definition of the zeta function, but we have the Euler product. It's a sum, it's a product over primes. The prime is that you want to be able to define things without also immediately giving a proof that they do in fact converge. So the prime is that just define this product, and if it doesn't converge, the answer is 0. Okay, give a junk value if it doesn't converge, and if it does converge, then this value should be the correct value. So that's what that prime is doing. It's called a T product and T sum. These are ways of allowing you to write things without worrying about convergence, giving you junk values if there is no convergence. Okay, so we have the Euler product formula. So if you take the logarithmic derivative, meaning zeta prime over zeta, I'll let you do the simple calculation that you get the Dirichlet series whose coefficients are the von Mangold function. And this we also have a proof of. This is that the L series whose coefficients are the von Mangold function at S is equal to negative the derivative of negative zeta prime over zeta. The L series is a sum, again, without worrying about whether it converges or not, of the nth term of the L series. And the nth term of the L series is 0 if n is equal to 0 and f of n over n to the s otherwise. So again, this is this issue with how you implement L series. Okay. Yeah.
How does the machine know the product is going to diverge so that it has to return 0?
So the way like a sum like this is a sum prime, the T sum. The way it's implemented is if the series converges, then make it the value, and if it doesn't, make it 0. So this summation comes with a question of whether or not it converges. So it might not be able to evaluate it until you give a proof of the convergence.
It's worse because here it's complex numbers, but if the sum were in something which is not Hausdorff, then there would be an arbitrary choice of a limit.
Yeah, yeah. I think here, so this is the co-compact filter. So however you leave compact sets with no.
The limits are not unique and non-Hausdorff spaces.
Yeah, yeah. Okay. All right. So we're going to use Perron's formula, which is that if you integrate y to the minus s over s over some vertical line with sigma greater than 0, you get 1 if y is less than 1 and 0 otherwise. It's an indicator function. This notation, this vertical integral notation means an integral from minus I infinity to plus I infinity. There are all kinds of issues with convergence with what I'm saying because I'm only dividing by s, and you all know that you can't integrate 1 over t. I guess I should have said somewhere that sigma is the real part of S and T is the imaginary part of S. Maybe not everyone reads Riemann's memoir every day, like number theorists. So when you do complex analysis, it's always Z is equal to X plus IY until you get to number theory, in which case it turns immediately to S is equal to sigma plus IT. And sorry, that's just how it is. Right, so I will ignore issues with convergence, but if you take that formula, so you take the Chebyshev function, you plug in, instead of summing over n less than x, you sum over all n, but now stick in this indicator function, put in the definition of the indicator function as this integral. In number theory, you see a sum and an integral, they always come in the wrong order, so you flip them. You flip the order, and you get an integral, a vertical integral over the Dirichlet series with von Mangold as its coefficients. And then you remember that that's what the logarithmic derivative of the zeta function is. And so now you get to this expression. So this is a simple way of connecting a sum over a series with an integral over the corresponding L function. Okay, so none of this is okay. The reason I'm not showing you any lean is because none of this converges, because I still only have 1 over s in the denominator. We're going to do something about that in a minute. But that's roughly the outline. Is there something you don't like?
No, just sorry, that's a lot.
Okay, it is a lot. So don't read anything here. You don't need to know anything about this. I'm just telling you what's going on. Oh, by the way, so at this point we certainly need that not just the real part is not just greater than 0, but actually greater than 1. Never mind, because again, none of this is okay. But the zeta function, as originally defined, is not the Riemann zeta function. This is the Riemann zeta function, because it gives the meromorphic continuation. So you have a theta series, and then you take a Snellen transform, and you divide by a gamma, yada yada. Here's some poles that you can read off. Again, you don't need to know any of this. I'm just throwing out a lot of facts that will, if you get into this project and you start chasing down definitions, you'll see some of these things, and I'll be around so we can talk about it. So forget what that was. We have the theorem that the zeta function, however it's analytically continued, is differentiable on the entire complex plane except at s equals 1. Okay, so we have the meromorphic continuation. So now we can talk about pulling contours. So what we have proved so far, and this was work with my postdoc Vlada Sedlacek, What we've proved is that in a region where the real part is at least some function of the height, so you take some height minus t to t, there is some constant a, which is, you know, in some reasonable range between 0 and a half, so that for any t at least 3, we can get, first of all, the holomorphicity of the logarithmic derivative of zeta, which means we know that in particular the denominator is not 0. In a rectangle, which goes from this 1 minus some constant over log t out to whatever 2, and then from minus t to t in the imaginary part, except of course at the point 1 where there's a pole, and we have bounds, uniform bounds in that region, which are again t to the 9. So the reason you're seeing t to the 9 and not t is because we're not doing Hadamard. When we do Hadamard, those 9s will go away. So just by elementary partial summation already gives you this much. Of course, you have to implement partial summation, which didn't exist in the library. Does partial summation now exist in the library? I know there was talk of Euler-Maclaurin summation. Did it make it in? Okay, we'll have to look. I don't remember if it made it into the library. So maybe this is now easier because the library's gotten built up since we proved it.
By partial summation, do you mean like what's called summation by, some people call summation?
Summation by parts. Yeah, summation by parts. Okay, so this bound is no good near 1 because we've pulled this vertical line. T is very large, so 1 minus a constant over log t is very small. We're very close to the 1 line when we go high, which means we have to do something to, we can't have uniform bounds near 1, so we just add another rectangle with an absolute number like 3. So in the small range, we just say, well, you're holomorphic. There exists some sigma naught, so that you're holomorphic in a little rectangle, and there you just use compactness to give you some bounds. Okay, so and then you just estimate the resulting integrals. You get the residue from the residue theorem for rectangles that we discussed at this point, and everything works out. Okay, how do you make all of this rigorous? Since we haven't been discussing what you do, so you can't do it with a 1 over s, so you stick in a little smoothing function. That smoothing function, so here's the kind of main theorem. When you stick in the smoothing function, which we cook up as a Mellin inverse transform of Mellin convolution, again, you don't need to know what those things are. What you get is an approximation to the indicator function. And so here's what the theorem looks like. You're given an arbitrary test function, smoothing f. You know that it's once continuously differentiable, once real continuously differentiable. So it's a C1 function. You know that it's non-negative. And you know that it's supported in 1/2 to 2, just to give yourself a little window around 1. You basically want to create a delta spike around 1. And you know that its total mass is 1. Okay, so so the function that you really want to work with is the indicator function. So this is the indicator function that x is between 0 and 1. This is 1. Okay, and then what we're going to do is take a bump function supported in 1/2 to 2, and there's another theorem that says such a thing exists. It's non-negative. It's at least once differentiable. And then with this epsilon, so what you do is kind of fun. I can't use psi, so let's use, what did I say? Eta, nu. So nu sub epsilon of x. This is kind of fun. It turns out the right thing to do is nu of x to the 1 over epsilon divided by epsilon. This is the right way to smooth things in the multiplicative positive reals. So that makes a function that looks like this, that's supported in something like 1 over 2 to the epsilon up to 2 to the epsilon. So it's very tight support, but of course that comes at a cost of the height. And once you stick that in, what you get for the smoothing function, so this is now called 1 epsilon. 1 epsilon looks like 1 and then drops down smoothly. And this happens around like 1 over 2 to the epsilon up to 2 to the epsilon, something like that. So that's what this function is. So the smooth Chebyshev function, given that smoothing function and the epsilon at x is this integral. And we've proved that it's equal to the Dirichlet series, which has von Mangold function times this smooth function at n over x. Okay, this is the content of this smooth Dirichlet theorem. Again, there's a lot of math going very quickly at you, and I don't assume you're all number theorists, so just ignore it. And this is like a pitch for the project, and what I really want to get to is show you how we use the blueprint and the Zulip. So if you're not following the math, it's okay.
So you drew a picture of what this function looks like. Is the coordinates definition, you sort of threw a bunch of names at us, or could I just take any smooth function that looks like your picture?
Yeah, that's exactly the point. You take, I haven't told you how to find such a thing, but I said if you give me a smooth function, it's once continuously differentiable, it's non-negative, and its support is in minus a half, and its total mass is 1. In the sense of integrating over the Haar measure of the multiplicative positive reals, which is dx over x. So that's just a normalization. Then you get this identity. That doesn't help you until you do something with it, but at least it gets you what yeah. I'm going to talk about the costs and the benefits of it right now. But at least mathematically we're okay, close enough to okay. So what you do with it, there's a cost, of course, which is that this thing is not the original function, but they differ. They differ by the length of the sum times the size of the individual points. And so Preston just PR'd this a week or two ago. Preston's here. So here's the statement, which again will look familiar. So there exists some constant, so that for all x at least 3, and for all epsilon between 0 and 1, and epsilon times x can't be too small, because then that will make this error term too small. Then the difference between the smooth version and the original Chebyshev function is bounded by epsilon x log x. Okay, so that's the cost of introducing the smoothing. The benefit of introducing the smoothing is that this smooth function decays like 1 over s. So now we have 1 over s squared. And now all the pulling contours past each other, interchanging order, summation, and integration is all kosher at the cost of an extra epsilon in the denominator. So that's this. This is the theorem melon of psi. I don't know why it's called psi. It should be called nu or something, whatever. This is a project that's been going on for a long time, and lots of different people contribute to it. And I let things in if the code compiles and the theorem does what it's supposed to. So this is what a really bad library looks like if Mathlib wasn't maintained by people trying to make perfect code. So what we'll have to do eventually is go through all of the code and just decide what of it can be cleaned up and bit by bit port it into Mathlib. That's something else we'll need to talk about. But anyway, so this melon transform, again, I haven't told you what that is. The melon transform of this new function at s is bounded by 1 over s. And here we're taking it at epsilon s, so it's going to be bounded by 1 over epsilon s. So it's a simple smoothing argument that will allow you to do all of these interval exchanges. And I think that's all I wanted to say about the mathematics and the big picture of what we're doing. And I was going to go to Blueprint. Any questions before I switch to that? Everything makes sense? Okay. So let me tell you what blueprints are and how they look and so on. Okay. So if you Google, I think if you just Google my name, let's see. Can I make this larger? How's that? Can you see that in the back? So if you just Google GitHub and Kontorovich, then okay, it's probably the first hit, and then the prime number theorem, and I don't know why and not plus is here. So this is, I can't understand anything that's on a page like this. It's just way too much information. But if you just ignore that information and scroll down, there's a Zulip channel and there's also a blueprint. So if you click on the blueprint link, this is where you're going to see all the fun things. So here's the first approach. which is the Wiener-Ikehara theorem. And you can click on that and you can read through all the Fourier analysis that was done and how it was all implemented and so on. So I'm going to close that because we want to go to the second approach. So here's the residue calculus. Everything here is in natural language and everything here is hyperlinked. So for example, if I scroll way down, here's Perron's formula. Here's all the things you have to do to get Perron's formula to work. Here's Mellin transforms. Let me scroll down to, okay, so here's a theorem that we don't yet have proved. And the reason I know we don't have it proved is because there's no check mark next to it. So here's this is the beginning of the partial summation argument, and it has a check mark. And the check mark means it's proved. And if I hover over the check mark, it has a little lean symbol there. Can you guys see that? The lean symbol. So if I click on the lean symbol, it pops up the name. You don't have to name the theorems by the same, you could have, definition of the Riemann zero function or something, but I like to have my names be exactly the same as the name in the lean, so that there's a correspondence. But anyway, so if you click on the lean button, it says, here's what it's called in lean, and it's called the same thing, Riemann zeta zero. But now I can click this. And if I click this, it takes me to the documentation. Well, that's not very useful documentation because all it says is a non-computable def that takes a natural number and a complex number and returns a complex number. But if you click on equation, then it says how it's actually defined. So it's a sum up to n plus 1 of 1 over n to the s, and then this integral. So this is an execution of summation by parts on the tail of the zeta function. And then if that's not good enough, you can click on the source. And if you click on the source, it takes you right to where it's proved. Now, here's something funny that you'll see, which is a little bit unique to our the way we've implemented the blueprint. Usually, the way people do blueprints is they have one text file, and they write a whole long text file, and then they open up a separate lean file, and they start to make the lean file look like the text file. And then you have to have two files open, and you want to coordinate the names and say this file is called that, and so on. And what we've done is we added these extra little delimiters. So this is with Ian Yauslin at Rutgers. We added these, the slash, what is this, the forward slash minus sign is, tells lean, this is going to be a long comment. So what we did is we made a forward slash minus sign and two ampersands, not ampersands, what are those called? Percents, just percents, and 2%, and percents look like comments in LaTeX. So that there's a little script that scrapes out all of anything between those delimiters and automatically generates the text. So that allows you to work in one file simultaneously, writing the natural language code. So this says, I'm going to write a definition. The definition is the Riemann zeta zero. Its label is also Riemann zeta zero, and its lean label is also Riemann zeta zero. So these are unfortunately extraneous. And the / lean OK says that the definition has been stated formally. And then I just write LaTeX. For any natural n greater than n, we define this thing, n definition. Immediately after that, I have the formal definition. And what this allows you to do, let me see if I can show it in action. Okay, of course I closed it. So let's get VS Code going. How's that? Can you see that in the back? So what this allows you to do is, if you have something like Copilot running in the background, and Copilot's really useful for things like this. I'm going to let it just load for a second. Copilot's really useful because it starts suggesting what it thinks the next line is. So for example, this log deriv zeta holomorphic large is one of the targets, and you can read in natural language right before it what it's supposed to say. So it's a lemma, and it says there's some constant a, so for all t greater than 3, this function zeta prime over zeta of s is holomorphic on this rectangle, except at 1. End lemma, and now in formal language, here's the statement, and then the proof is, well, sorry, but here's the natural language proof, and it says what it uses. It uses zeta zero free. And so what that will do when we get to the blueprint, so let me back out of the source, back out of the documentation. Now we're in the blueprint. This is sort of the best part of the blueprint is, okay, there's all these theorems. It's kind of hard to wrap your mind around what's going on. there's a dependency graph. And the dependency graph is automatically generated. And let's see, if I zoom in, so here's the medium prime number theorem, and you can click on it. I just clicked on it, and it told me what the statement is that we're headed for. And I can click on the tech, or so this is what we were just looking at, this log deriv zeta holomorphic large T. If I click on that, again, it tells me the natural language. I can also click on the lean, and it'll take me to what the statement is. That's the statement. It doesn't yet have a proof. If I click on source, it takes us right to where we were just looking. But the fact that I said it uses zeta zero free means that in the dependency graph, there's going to be an arrow from zeta zero free to this thing that's automatically generated. And here we can see, we proved this zero free region for the zeta function. And again, you can click on the lean, or you can click on the tech and see where that is. Okay. Yes.
If you go back to the graph.
Back to the graph.
Yeah. What's the difference between different color codes?
Great. So the coloring tells you what's done, ready to be done, or in the process of being done. So squares are definitions. So that's just a definition. So it's a square. Any lemma theorem, anything like that, is a circle. And it gets a green background when it has been stated formally. And it gets a green interior when it's been proved formally. So it's very quick. It's very easy to just jump your eye right to, oh, these are the leaves that need to get done next. We need to prove this. We need to prove this. We need to prove this. This hasn't even been stated formally. Actually, it has. I don't know why it still has. There's a missing lean OK to say it has been stated formally, but it's not ready to be proved. These things are ready to be proved because all of the prerequisites have been formalized. Yes?
Can we customize this legend in our?
You absolutely can, and this is not the standard legend. This is already customized. So it is possible to do. I don't know how to do it, but I'm sure an LLM can tell us how. I thought there was at least one thing here that was, yeah, here we go. So here's this Wiener-Ikehara theorem double prime is light green. That means it's actually been proved formally. It's been proved formally, assuming the statement of the auto-Chebyshev, auto-Chebby bound, which has not yet been proved. So that's why it's not really done, because this, once you start proving this, you might realize, oh, I needed to add another assumption, or oh, I needed to change the statement ever so slightly. So that's why it's been proved. It assumes things that have not been proved, and so if you want to recurse back up to there. There are a couple of stragglers here. Yeah, this is looking to Dedekind eta functions and Dedekind zeta functions and Chebotarev. So that stuff is kind of not ready to go into the library. We also have, if you want to do the prime number theorem in progressions, you can do that. There's also consequences of, so here's the weak prime number theorem. This is what was finished back in March, just with little o, March of 2024, just with a little o. And then as a result of that, we've proved all kinds of things. If you just want to sum the primes, or if you want to know what the prime counting function is, here's an alternate version of that. And then here's this hasn't been done. So the asymptotic for the nth prime number is a function of the fact that you know the prime number theorem. Now, how do you keep track of everything that's going on? Okay, that's a big dependency graph. There's a whole lot of people who might want to work on it. Let's say you start working on this leaf, but so does somebody else and you don't even know. So this is where Zulip comes in. We're going to coordinate all of our activities. Zulip likes to go to sleep for some reason. Please. Let's just try from scratch.
Alex, while we wait.
Yes, please.
Patrick Masseau is the author of the.
Patrick Masseau is the author of the Blueprint Technology. Absolutely right. Last time I said Masseau and it was Masseau Miller, but this is just Masseau. Okay, great.
Do you find this used in LaTeX?
Do I find?
Write this used in LaTeX, so
In LaTeX, you write whatever you want. It's natural language.
it's not generated by me what it uses.
No, although Copilot, so when I write a natural language proof, Copilot starts suggesting the formal proof, and similarly with the statements. Yeah, I'll try to show you that too. Let me just finish the thought about Okay, so we have our secret hidden Simon's 2025 area. And inside of that, we have secret outstanding tasks, which take you to a list of tasks. So here's how you play with this. So I've written here a bunch of leaves, and you can click on any leaf, like Riemann zeta residue. If you click on that, it takes you to the statement. We want to prove that the zeta function has a residue of 1. In particular, we want to show that zeta of s minus 1 over s minus 1 is bounded in a neighborhood of 1. There's a natural language proof. This is almost in Mathlib, but it's going to take a little bit of work to get from what's in Mathlib to the real thing. And again, you can click on lean, and here it is. Here's the statement that the Riemann zeta function minus the function 1 over s minus 1 is big O neighborhoods within 1, except not including 1. That the residue is 1. So that statement is there. And if you want to, I claim task 1, and I'm going to post this. And that means now everyone can see that I'm going to work on task 1 and nobody else should work on task 1. Don't waste your time working on task 1. So you go on to Zulip and you say, you know, I want to work on this. Then I'm going to change it to here, claimed by, well, I would put the person's name. I don't know, this is kind of silly, claimed by me. And then I save, and now it says claimed by so-and-so. And you can click through what the previous versions of this were. The previous versions were not secret, they were for everybody. So people claimed it, and then they finished it. And then you can go through and see, you know, there's a long history of all the various things that have happened. Here's a whole lot of stuff. Here's what needs to get done. This was done, yada, yada. So again, let me go back here, and there we are. So if you are so inclined, you're welcome to claim one of these tasks and jump in. And maybe there's going to be a little group of people who want to finish off the proof. I think we can finish it this week. If we actually put like a good 3 or 4 days to it, we're close enough that that would be pretty cool to lock this in. But anyway, so there's a bunch of tasks there. I told you about the blueprint technology of Patrick Massot, which helps organize things, helps you see what's going on. This is another thing about this. I should point out is that it's a really cool way to collaborate. There have already been, I think, 24 collaborators on this project. The vast majority of whom are people I've never met before and probably never will meet, and maybe they're not even mathematicians. They're like, yeah, the 28 collaborators, like 28 contributors. Okay, so these are people around the world who, somebody's an engineer, and in his spare time on a weekend, he said, okay, I'm gonna do one of these calculus things that's left there. Anyway, this is not so important. So it's really fun in a way that you can collaborate with people where you don't have to trust them. I don't need to know that this engineer knows calculus or not. Lean says, I gave a target, and Lean says the target was satisfied. So it's kind of great. It's anyway, there are a lot of people here of whom I think I only know maybe I know 10 of these people. All right. I think I'll stop there. Thanks.
I have a stupid,
Yeah.
very practical question.
Please.
So your LaTeX
Scraper.
script, whatever. So first of all, is it usable by everyone? I mean, how does this work? You import it in the lake file or in the blueprint? Great
question. The way it works is you get a colleague named Ian Yausling who knows how to do these things. And you scroll down and you say the use of LaTeX inside Lean is done like this. And where's our link? Did someone change this? Quick contributions. Oh no. There used to be a link here for how to set this up yourself. Okay, so let me
Copilot took it away.
Git blame.
Yeah, git blame. Here we go. Ian, complex analysis. Ian, Pythagoras. Oh my God, I don't know where it is. Okay, I have to find where it is, but it's a tiny little script that does the scraping.
You add it to your blueprint.
That's right. It exists somewhere here. Maybe it's this GitHub workflow or something.
And then the second question related to this. So when does compilation actually happen? So concretely, if I make a LaTeX error, when do I get the error message?
This is the annoying thing. This is actually one thing where if someone's actually writing the blueprint, then I have to look very carefully at what they're doing. Because if they make an error, I won't see it until the CI is not checking LaTeX.
Oh, okay, so it simply doesn't render.
If so, you won't see it. The only way to get the blueprint to run once it's in GitHub, there is a way to get blueprint to run locally. I have seen it before. I don't remember how to do it, but when I work on this stuff, I always do a pull request for myself. I merge it, and then 20 minutes later, I go and look at the blueprint and make sure I didn't do something stupid that ruined everything.
Ah, okay.
So it's that's a slightly frustrating aspect that I'm sure can be fixed. It's just I don't have the chops to fix it. But yeah, I'm with the blueprint. I'm careful not to just.
Because I mean, on the other hand, if you use a usual LaTeX, I agree that it's painful to have two files open. But on the other hand, I mean, if I have a LaTeX file, I just click, and if I make
that's right.
a LaTeX mistake, I see it immediately.
That's right. So there is somewhere locally, I think there is a way to generate that blueprint. I just don't remember what that is, and I thought we had those instructions here, although I don't.
Lean blueprint extract.
Lean group, okay.
And yeah.
And maybe this is the README.
Yeah.
Okay. Yes, thank you. Thank you.
At any rate, I would have expected your answer to be, no, just ask an LLM if your LaTeX code is correct.
Well, my local LLM is Ian Yauslin, and if he's not around, then I ask an LLM. But yeah, so the file that I was looking for is right here. Thank you. So this is the file I was expecting to see, which explains how to do this extraction tool. And I also wanted to show you, now that it's done compiling, that if I just put my cursor here and I have Copilot running, the proofs it's not good at. But if I've said something in natural language, like let's see, if I exit this out, and my cursor is sitting here, do I have Copilot running? I think so. It should be running. Of course, whenever you try to do an experiment live, it never works, but it often will start auto-generating. I don't know if it's the Wi-Fi here or what, but it will often start auto-generating the formal statement of this lemma once it has the statement right next to it. It's learned that that's how I use the system. Other questions, comments? Yeah.
So kind of like Mathlib wants to be as general as possible.
Yes.
Would it, because I guess you could do like the prime number theorem for like L functions of like the Selberg class. Would that need to be formalized?
So I think I'm making them out to be worse than we have many of the maintainers here. They're reasonable people. You know, if you say, look, I proved the prime number theorem for the primes in the rational integers, they'll say, okay, fine, let's put that in too. But then later on, you'll do it for the Selberg class, or you'll do it for, you know, Dedekind zeta functions, and then that'll just supersede the previous work. Is that a more accurate representation of Mathlib? It's reasonable people, but just, you know, if someone's proving 1 + 2 = 3, that's not something you want in the library.